Hello, Physics 20s. I'm going to spend a minute on horizontal and circular motion, and I made some quick notes that I can do some work on. So you do need to know both kinds of circular motion. I think the horizontal one is the easiest. That's just where typically you have one force that will be causing you to go in a horizontal circle, kind of like a merry-go-round, or I guess if you were to, like spin something horizontally over your head, like a lasso or something like that, but it would be in the horizontal direction. So in that case, the if it is on the ground, the one example I noted is that the normal force would cancel out the force of gravity. So I'm going to give you one example here. This is I it's kind of a classic one because it relates to us. So you can see this map here. This is a map of Fort Macleod. If you come south on Highway number 2 towards Fort Macleod, this is the interchange you have right here. And years ago, this specific exit ramp was causing all kinds of problems because people were taking it too fast. Truckers were going right off the highway. Um, it's a really flat exit, and um, in looking at the map, you can see why they couldn't take the exit and make it really big and get a nice exit. The reason you can't do that is because of this railroad. There's a railroad running right here that prevented them from making a nice big exit ramp so they could keep the speed really high. So kind of, I've never measured this, but I've always driven by it and kind of eyeballed it. So um, you'll notice that as you come in here, there's rumble strips on the highway. There's a bunch of signs that say slow down. The exit speed that's posted is 60 kilometers per hour, and it shows a truck tipping over and there's a whole bunch of signs saying turn, turn, turn. Especially once you get under the bridge and you come through this part right there. So anyway, I'm going to estimate that right in here in this curve, we're going to estimate that right there, that radius, okay, that radius we're going to say is about 100 meters, okay, for that turn. And the question I'm posing here is, oh, I said 100 kilograms. I guess it could have been 1,000. You'll see the mass doesn't really matter. 100-kilogram car is not very much. That's like 4 sacks of potatoes there. Anyway, um, the the car, I want to know the maximum speed it can go around this corner before static friction will no longer hold it to the road. So the tires are turning on the asphalt in this case, and if it goes too fast, then inertia will just carry it right off the road. Okay, so it gives me the turning radius, and it also tells me the coefficient of static friction is 0.6 between the tires and the road. Okay, so um, what I want you to see here is this is our setup. We will say that the force centripetal at its maximum, the centripetal force will equal the force of static friction. Okay, because if the friction isn't strong enough, then the centripetal force won't be strong enough to keep the car going in a circle. So this is what I mean by um, the centripetal force is just being caused by one force, okay? And that's what typically happens in horizontal circular motion. So if we expand centripetal force, remember you have two formulas for centripetal force. You could also use m4 pi squared r over t squared. We could use that one if I was given the period, or if which I wasn't. So because I'm trying to find the speed, I'm going to use the other one. Okay. So the expansion shows mv squared over r will equal mu s, the coefficient of static friction, times the normal force. But the normal force will be equal and opposite the force of gravity. Okay. The normal force is always up, and if it's horizontal, that's what I meant earlier, that the force of gravity would be straight down. So what I need you to see here, and I didn't do any more steps than this, to this point, we need to solve for the velocity. And what's clever in a lot of these circular motion questions is that the masses are going to be the same on both sides. So it means we can get rid of them. Okay. So that really leaves me then with v squared over r is equal to mu s times g. And if I'm trying to solve for v, then v would just equal the square root of mu s times g times r. Okay. And using, I know I really blew this up here, but using the numbers that are here, the mass of the car didn't matter because it canceled out. So really I just have R is 100, G is 9.81, and mu S is 0.6. And if I do that really carefully, then I wind up getting, it's actually 24.3 meters per second. Now, 24.3 meters per second, that doesn't really register for me anyway, because most of us don't think in terms of meters per second. So I did a conversion. I converted it from meters per second to kilometers per hour. You would have multiplied that number by 3,600 and then divided it by 1,000, if you remember the conversion process. And anyway, that winds up being 87.3 kilometers per hour. Okay. Now, obviously, I grabbed that 0.6, the coefficient of static friction. I grabbed that from a reference. So I'm not sure if that's exactly what the coefficient of friction would be on that corner. But the point is that you cannot exceed 87.3 kilometers per hour if that curve was completely flat. Because if you go faster than that, then what'll happen is friction won't hold you and you'll just go flying off the road, something like that. Okay. Now, as an engineer, if you actually determined that that was the maximum speed, well, you wouldn't post that as you wouldn't put up a sign that says maximum speed 87 kilometers an hour. It's like, that sounds weird. Because due to safety reasons, anyone who saw that as the maximum speed would easily go over that. And so I'm confident there's some safety margins that engineers would design these roads under, which in my mind makes sense that a posted speed limit of 60 kilometers per hour is much safer than saying 87. Okay. And obviously, the road conditions can change a lot. Like if you were too close to the side, you could hit gravel and then the coefficient would drop a lot. And then all of a sudden you'd be in big trouble. So, but just as an example, I wanted you to see that if you know it's a horizontal problem, it's likely the centripetal force will likely be caused by one force. Where things get a little more complicated, just a little bit, is when you look at vertical circular motion. So as I noted here, you have to consider two forces that are causing the object to move. The force of gravity and the force of tension, or the normal force. Now, I'm just going to come down here to show you the formula summaries, and I'll actually kind of sketch them first too. So let's do the mass on a string. Okay, so if this is the center of our circle and we have a mass that's on that string, it will, of course, we'll say that it goes around in a circle like this. Okay, and vertically, all we really look at is the object at the very top or the very bottom. Okay, because on the sides it gets a little complicated. The forces are kind of perpendicular to each other. So it's a lot cleaner, and we really only consider the top and the bottom. So let's look at the top first. At the top, the force of gravity is always straight down. And also in this case, there would be tension. Okay, so those two forces would be acting downward, okay, if you were swinging it over your head. And what we look at then is there's a net force. There's a sum. Both of these forces are going to add together. Now you have two forces that are going to cause the mass to keep going in a circle, at least right at that position, right? Like, I mean, if you're looking at the side here, gravity is always down. So on the side, and the tension would be in. So but that gets a little more complicated, and obviously there's degrees and angles all the way through this if we're really breaking down the movement of this object. So all we look at is the top and the bottom. So the summary then is this, that at the top there is going to be a net force. Okay, and that net force is really going to be Fc. Fc is going to be the net force. The centripetal force is the sum, in this case, of the two forces. So here then we have Fg plus Ft. Okay? Now, when you look at the bottom, though, when it gets to the bottom of the circle, in fact, you know what? Let's just clear this all out, and I'll draw it again for the bottom. So at the bottom of the circle, okay, so we have this is your motion. The mass is now at the bottom. And if we analyze the forces here now, gravity is down, Fg, and then but now the tension is up. And I'm drawing this a lot bigger on purpose because the tension has to match gravity and then be even greater than gravity to keep the mass moving towards the center. I mean, you can imagine if the tension was equal to the force of gravity at that point, then the mass would just keep going horizontally because there isn't an unbalanced force acting on it to try and pull it into the center. So, but that isn't happening. So what happens here is now the net force is still going to be towards the center, but it's going to be the sum of these two forces, of the of the tension up and then the force of gravity down. So we still get the same formula, of course, but the important difference is something we will now address. So let's come back to the top. So at the top of the circle, the centripetal force or the net force is down, the force of gravity is down, and the tension is down. Okay. So if you forget this aspect, you'll still get the answer right because everything's in the same direction. So if you didn't assign them as a negatives and you left them all positives, it'll still work. Okay. So as noted above, in the top of the circle, everything is pointing down, and I like to put arrows beside those, okay, to remind me at the top of the circle, all the forces are pointing down. Now at the bottom of the circle, things have changed for some of them. The gravity is still down at the bottom. That never changes. But at the bottom, as you can see here, the centripetal force is actually up and the tension is up, okay? So the pulling force from the cable or the rope is up. Why that's important is you do need to assign positives and negatives for sure. And we'll do one example of each. Now, I could have also drawn, I also made this to the right here. What do we do for a loop-the-loop? Well, a loop-the-loop is a little bit different because instead of tension, here, let me just make some room here. Instead of tension in a cable or in a string, we don't have any tension, but what we do have is the track itself. So if you had a nice loop-the-loop, like something like that, and you get a marble in there and send it through, well, it'll obviously go through the loop, but we'll consider its position right at the top and right at the bottom. Same thing, okay? And if you note, at the top of the circle, everything is still down, but we don't have tension now. What I want you to see is the track itself. The track exerts a pushing force on the marble to push it into a circle. So you think about it, if the loop wasn't there, the marble would just go in a straight line. But so in effect, the normal force keeps pushing towards the center all the time, okay? The track pushes instead of there being a string attached, okay? So, but the normal force is still down at the very top, okay? And at the bottom, the normal force is up, okay? So it looks very similar to what we just did for the mass on a string, okay? So actually here what I'd like to do is maybe I'd like to show you question number, let's do question number 4 on the worksheet here. So you can see that up here. Let me just come up to it again. So here we have the marble is going down the ramp, and at the instant it is at the top of the loop, the force the loop exerts on the marble is equal to 0. Okay, so all we know is that the marble at that speed is going 5.4 meters per second, and it wants us to determine the radius. Okay, so let's actually look at that right here. Let's maybe do this right here. So at the top, at the top of the loop, the mass is here, but it's moving at 5.47 meters per second right there. Okay, and it does say that the force that the track exerts on the marble is 0. That's really important to catch, because that means that the normal force is equal to 0. Okay, so if we consider, firstly, if you look at this question, is this vertical circular motion or not? Yes, it is. So that means that we have to use the vertical circular motion formula, either Fg plus Ft or Fg plus Fn. We only look at tension or the normal force. So in this case, the normal force is equal to 0. So that just crosses out. And when you get a question like this, what I want you to see is we can expand both of these. Again, I'm going to use mv squared over r because I'm looking for the radius here, and I was given the velocity. I'm not using the period. I haven't given you one of those yet, okay? But because they're at the top of the circle, everything is pointing down. And in this case, when I expand them, it's now mv squared over r equals mg. And I think what a lot of you are catching already, you can start anticipating this. I wasn't given the mass of the bob or the object, but that's okay because it disappears. Woohoo! So I can now solve for v by getting the, or sorry, not for v. I wasn't solving for v. I'm solving for the radius. So the radius will equal v squared over g. Okay, and that 5.47 squared divided by 9.81 is equal to 3.05. Okay, so there I determined the radius for a vertical circular motion, and in this case, this was a mass going through a loop-the-loop, and the normal force was 0. Okay, so really it's as if it's just coasting through the top of the loop, and it's just barely passing through, okay, without falling off. Okay, so you want to in situations like that, yes, you don't want to fall off, but if you're in a roller coaster or something like that, but you can imagine swinging a pail of water over your head and just swing it just slow enough that the water doesn't fall out of the bucket, but that it keeps going in a circle, something like that. Okay, so let's do a different one that's actually at the bottom. Okay, the bottom of a loop. So I'm just going to make some space here, but we'll come back to this and use the same space. So the question I wanted to do was number 7 on the review. So number 7, I'll just pull that up here again. This one, get there in the middle, not what's in green, but underneath it. So at the bottom of the arc, a pendulum bob has a speed of 6.2 meters per second. if the radius of the pendulum's path is 2.75, as the bob moves through its lowest point, the tension in the string that supports the pendulum bob will be how many times greater the magnitude of the force of gravity on the ball. Okay, so I'll have you look at that, but let me just switch to the other screen here so that you can see how we would tackle that question. Okay, so what we've really got here is we've got this is a pendulum bob, so it's swinging through the lowest point like something like this. And at that point, it is going in to be a tangential velocity, that's 6.2 meters per second. And at this point, here it's experiencing tension up and gravity down. Okay. And those two will combine to make a net force. I realize I didn't know if I said that before, but the net force will equal the centripetal force, which is really the result of these two. Okay. Now, at the bottom, though, this is where we got to pay attention. At the bottom, the centripetal force is up, like the net force. Okay, so the sum of both of those added together would give you the net force. It would be up. Gravity's down, and the tension is up. Okay, sorry, I'm kind of confusing with all that other stuff. So, this is a trickier question because it doesn't give us a mass. Okay, and the what can make a question like this easy is if you just assume a mass. The question, you remember, wanted to know how many times greater is tension than the force of gravity. So how many times greater is the tension up compared to gravity down? So what we can do is assume 1 kilogram. This is one way to do this. It's probably the most direct way. So if we assume 1 kilogram, then we can say mv squared over r is equal to mg plus ft. Now, obviously, we don't have a formula for tension directly, but we can find it indirectly. Now, there's something really important here, and that is the centripetal force is up, but the force of gravity is down. So we need to make that negative. And if you miss that detail on here, then you'll just get the opposite answer. So really, if we're going to solve for the tension, what we have to do is add the force of gravity. So really we have mv squared over r plus mg is equal to ft. Okay, and substituting in 1 kilogram for m, it looks ugly. 1 kilogram for m, and the velocity in this question is 6.2 meters per second. And so that'll get squared. We divide that by the radius, which it gave us, 2.75. And that's going to be obviously times 1 kilogram, plus 1 kilogram times 9.81. Okay, that's going to equal 23.78 or 79 basically, and that will be newtons. Okay, 23.79 newtons. So that's what the force of tension will equal. Now, that isn't what the answer wanted, though. Of course, that's how much tension there'd be for 1 kilogram, right? If it was 2 kilograms or 10 kilograms, it would be more. But remember, the question just wanted to know how many times greater is tension than the force due to gravity, or really the weight. Okay, so what would the weight be? Well, the force of gravity would just be mass times gravity, and in this case, that would be 9.81 newtons. So then tension is how many times greater? We would just divide 23.79 newtons divided by 9.81, and the newtons will cancel, and maybe bring it up here a little bit. Then the tension will be 2.42 times greater than the force of gravity acting down on it. Okay, so if that helps you too, when you're swinging on a swing, at what point when you're swinging do you feel the heaviest? And it's when you're at the bottom. That's when the tension up is the greatest. In fact, I always smile at the America's Funniest Home videos. Anytime someone is on a swing and it breaks, guess when it breaks? It breaks when they're coming at the bottom. It never breaks when they're way up on one side or way up on the other side. It breaks just either right after they pass through the bottom where the tension's the greatest. That's when the chain or the rope fails, because whoa, that's when the tension up has to be the greatest. Anyway, I hope that's helpful in tackling those. There are some tricky ones, so make sure you post questions to me if you have any questions.